Today's lecture is lecture number 16, and this is regarding binary erasure channel. And in this case, we will also see some of the examples. So earlier we have studied regarding binary symmetric channel, right? BSC. So this is BEC, binary erasure channel. This is another kind of special channel, and this channel is very much realistic. So again, we have some of the terms common here. One is binary and a channel. So this is basically a binary channel. So I have indicated some arrows here. And these arrows originate from the input. So X represents the input, the set of input symbols. For example, since this is a binary, we have 1 and 0. And then at the output, of course, we will be having the symbols like 1 or 0. When we transmit 1 through this channel, which is indicated by blue lines, this may appear at the output as it is. The 1 which is transmitted may appear at the output, which is Y, represented as Y. It may be 1 itself with certain probability, 1 minus PE. Or the transmitted 1 may reach the output as a question mark. I mean, we don't know what it is. The receiver doesn't know what it is. In another instance, if a 0 was transmitted, then that may appear at the receiver, Y, as a 0 itself without any error. Then the probability of this event occurring is 1 minus PE. Instead, a 0 transmission may result in something unpredictable 1, a question mark, at the receiver with the probability of PE. So altogether, we have the input, which is a binary, 0 or 1, and we will be transmitting this binary data through a channel, which is called as an erasure channel, here mentioned as erasure channel. And that results in the output such as 1 or 0. Sometimes some unpredictable 1. We do not know whether it is 1 or 0. That is due to error. So PE indicates the probability of error. 1 is transmitted due to some probability, maybe 30% probability. It may appear as something maybe not 1 or 0. The receiver cannot predict whether it is 1 or 0. Or when 0 is transmitted with the same probability, maybe 30%, it will appear at the receiver as something else. This cannot be predicted by the receiver whether it was 1 or 0. That is due to error, because when the signal was transmitted through the channel, maybe the channel has corrupted the signal and receiver cannot identify what it was. And other instances, for example, 1 was transmitted and that will be received by the receiver as 1 itself correctly with some probability, 1 minus P, maybe 70% probability. Similarly, when 0 was transmitted, that will be received by the receiver as 0 itself, and the receiver can identify that it is 0. And also, it can understand that 0 was transmitted and 0 was received. That with the probability of 1 minus P, maybe 70%. These numbers are just an examples. But this is not the entire characteristic of binary erasure channel. So if it is received properly, for example, 1 was transmitted and you receive it as 1, or 0 was transmitted and you receive it as 0, that's fine. In other cases, for example, 1 or 0 was transmitted and the receiver is in a confusion whether it was 1 or 0. In that case, since the receiver cannot identify what the signal was, in that case, receiver will send a feedback to the transmitter to retransmit it. And then transmitter starts retransmitting. Then again, during this retransmission at some other time, the transmitted symbol may be received by the receiver with 100% success, or maybe again with the confusion. It cannot decode again. So again, it will ask for the retransmission, and the transmitter will retransmit it. But again, we have the same scenario. Either the receiver may receive it, or receiver may be still under confusion whether what was the transmitted signal. So this process continues, that is sending a feedback from the receiver to the transmitter, and the transmitter retransmitting the message or symbol, and receiver trying to decode it. This process continues until the receiver comes to a clear conclusion that whether the transmitted bit was 1 or 0. So basically this is can be also defined as an errorless channel, because even if there is error, the receiver cannot identify what was transmitted. A receiver will ask for retransmission using a feedback channel, then transmitter will retransmit it, and this process continues until the receiver comes to a definite conclusion whether 1 was transmitted or 0 was transmitted. So as a result, we can say this as errorless channel, or it's also, primarily called as erasure channel. So why do we use the word erasure? It erases the error. There was an error here. That error was not clearly decoded due to this error, the symbol was not clearly decoded by the receiver. As a result, there were retransmissions until the receiver could actually decode the information. So as a result, all the errors that were there in the channel were erased after subsequent transmissions. So that's why we call it as binary erasure channel. So basically it wipes out or erases any error that has occurred during the transmission by multiple transmissions using a feedback channel. And we use the word binary here because we are dealing with the binary information, either 0 or 1. So this is a real-time channel, I call it as, because we'll see here, because if you consider a internet scenario right now, what is there in internet? When we transmit the data from our computer to somewhere else, and there are some protocols, right? TCP, TCP. Okay, so basically this internet, what we call TCP/IP protocol stack, that uses kind of mechanism. In general speaking, it uses this binary erasure kind of setting or principle, because when the data is transmitted, this may be received by the receiver properly or not. If it is not received properly by the receiver, then receiver will ask for retransmission. So the transmitter will again transmit, and this process continues until predefined number of times, or until the receiver can decode it properly. This process continues. So the best example is for binary erasure channel is the internet itself in a broad sense. Okay, so right now everything is internet based, right? Our communication. So that's the best example for, in general, for binary erasure channel. Okay, now we will see some more formal definition of binary eraser channel. So in the previous slide, I gave you the outset of a binary eraser channel, how we can represent the information. Here we have the definition. So in case of binary eraser channel, which is also called as BEC, there are two inputs because this is binary. So either 0 or 1. And there are more than 2 outputs. In this case, we had 3 outputs. So that is 0 or 1 or something else, which is neither 0 nor 1 as predicted by the receiver. The symbol here, the question mark, indicates that is due to some noise in the channel, no definition decision can be made. Either it was symbol 0 or 1, the receiver could not make a proper decision. That leads to retransmissions. Okay. In practical scenarios, if the receiver cannot decide 0 or 1, then it asks for retransmissions. How many times retransmission? Until the received symbol under question mark or with confusion is decided as 0 or 1. So the receiver should understand whether that question mark or whether that confusion, was it a 0 or 1? It should come to a conclusion. Until then, the retransmission will take place. That is in general. But in an internet scenario, if you consider TCP protocol, all this, that need not be the case. It will start to retransmit until predefined number of times, maybe 10 times, or I just set a number. Okay, predefined number of times it is going to retransmit, and if the receiver cannot decide what was that, then it is not the job of the transmitter to make the receiver understand. Transmitter will try to retransmit so many number of times, maybe x number of times, x is a number, and if the receiver can understand, it's okay, otherwise just leave it. So that's what it happens in internet, I mean specific cases. Okay, now this requires an explicit feedback channel. So along with the transmission channel, we also need a feedback channel. So why do we need the feedback channel? That is because the receiver wants to convey the transmitter that there was an error. I could not understand whether what was transmitted. I still having a question mark whether it was 1 or 0. So tell me, what did you transmit? So then the transmitter will retransmit using its main channel. Okay, then receiver will feedback. Okay, I understood, it was 1, right? Okay, yes. So to do that communication, we need the feedback channel. So we need the main channel, that is the binary eraser channel through which the communication takes place, transmission of 0 or transmission of 1. Additionally, we also need a feedback channel. So this feedback channel can have a very minute bandwidth, because we will be sending just the control information, whether it was received or not, all those. So that is the requirement here. Maybe you can call it as a burden here, because we need a feedback channel. That's an additional requirement. Okay, now you will see some of the features of this binary eraser channel. So BEC, binary eraser channel, ensures 100% correct data recovery. Why? Because receiver keeps feedbacking the transmitter that I have not received properly, or still it's a question mark. I cannot decode whether it was 0 or 1. So this process continues until the receiver can properly decide whether it was 0 or 1. So after that, we have received, I mean the receiver has received all the data with confidence or correctly. So that's why we call it as 100% correct data recovery is possible, or it can erase the errors in subsequent transmissions. It can try to overcome the error. So BEC is also a symmetric channel. So we talked about binary symmetric channel in our previous lectures, and we also solved some questions based on PSC. So there we use the term symmetric channel. So binary symmetric channel, where that word symmetry, from where that symmetry comes from. Can someone answer? Okay, no problem. So symmetry comes from here. You transmit with probability PE, one symbol, or you have an error in probability 1 minus E. So these two, PE and 1 minus PE. With one probability, 1 minus PE, you transmit successfully. With the other probability, P, that is 1 minus PE, here, you transmit it as something else. Similarly here, you have PE and 1 minus PE. This term will lead to some error, the other one will lead to success, right? So that's the idea of symmetry. If you consider total probability as 1, and if you say P or PA or PX something as the probability of successful transmission, then 1 minus that P or PA whatever becomes the probability of something else, right? Maybe you transmit 1, you receive it as 0, or you transmit 0, you receive it as 1. So that's the error, right? So that's why we call it as a symmetry channel. Okay, then if Px0, I mean probability of transmission is 0. Transmitting 0 is equal to A, then probability of transmitting 1 is 1 minus a. So one symbol is transmitted maybe 0 with probability a, then other symbol, that's 1, will be transmitted with 1 minus a. So if 1 is transmitted with the probability of 1 minus a and it is received correctly with probability of some p, then it is received wrongly with the probability of something else, 1 minus p. So that's the idea of symmetric. So one is p, 1 minus p, or 1 pi, 1 minus pi, and so on. Okay, then how to write it? Entropy. Entropy, you know the common equation of entropy, right? Pi log 1 by pi. Probability log of 1 by probability gives us the entropy. So this is the general representation of entropy if we know the probabilities. Since we know the probabilities here, where x represents a random variable to represent any input, maybe 0 or 1, then the probabilities we know. Input being 0 is a, that's the probability, and probability of input being 1 is 1 minus a. So just we substitute here to get the entropy. And next, the channel capacity of BEC, binary eraser channel, is given by this equation. So channel capacity is equal to, you know this term, right? Mutual information between x and y, the input and output occurring together. So that the channel capacity is equal to maximum of the mutual information between x and y for various probabilities, because we have different probabilities for x, right? So if you're transmitting 0, then we have a probability PE or PA, and if you're transmitting 1, we have a probability 1 minus PA or PI, whatever. So when you consider these cases, you get different values for I of x comma y for different values of x, right? In that you choose one that gives the maximum. That is the maximum channel capacity. So for different values of x as well as y, because for different values of x we have different values for y, you find the mutual information. So first, mutual information 1 for specific value of x. Next, mutual information 2 for some other value of x. X is 0, x is 1. And then find out what is ixy. First case, ixy, second case, and so on. And then finally, take out the maximum of these all ixy1, ixy2, these two. And choose that maximum that gives the channel capacity. So many bits per symbol. So that is the equation for channel capacity of this BEC, binary ratio channel. And now you need to remember some of these relations or equations. Actually, we have already solved some of the questions earlier. Those same relations we will be using here. So I think now you have a practice of using those equations. But today, after this discussion, we will be solving some questions on this binary eraser channel. So if you are practicing this at home, I mean these questions along with me, trying to solve, then these equations will be useful. Otherwise, you just refer back to the previous lectures where we have these equations. First one, conditional probability of y. How to find out that? When you know the channel, you can find out the binary channel matrix from the transition probabilities. That gives PYX, that is the conditional probability of the output, if we know the probability of inputs. So I guess you have solved many problems previously, and where we have found this PYX. Basically, a channel is given, then we will identify from x1 to y1 what is the probability. X1 to something like this, I will write here. There is a channel given. So these are the 2 points from where we insert the inputs, and these are the 2 points where we collect the output. I'm writing a simple channel here. So for example, this is x1 and this is x2, second input. Of course, these are binary. So maybe this is 0 and this is 1. And these are the output points here. One is y1 and the other one is y2 here. And when we transmit from x1 to y1, you have some probability, maybe 0.2, right? 0.2. And then we transmit the same 0, then it may appear something else at y2 with a probability of 0.8, right? 0.8. Okay, then similarly we transmit from the second input x2 to the output. So at the y1 point, it may appear as 1 itself with a probability of 0.5. So x2 transmitted will be received by y2 as 0 itself, or maybe not 0, other one 1. I mean either correctly received or not correctly received with a probability of 0.5 itself. Okay, so when this kind of matrix we have seen earlier, how to write p y x. So that is basically we write a matrix this way, where we have x1, x2 here and y1, y2 here, right? And we write down x1 to y1, the value is 0.2. So we write that 0.2 here. And x1 to x1 to y1 is 0.2, that will be written here. And then x1 to y2 is 0.8, that we write here, 0.8. So similarly, we continue the other parts. So that is how we find out p y x. So this we have seen in more detail. Okay. Then coming to the point of entropy of the input. So entropy is represented by this general equation, that is we have a minus sign here. Probability log of probability, the minus sign. So this is for the inputs, because we know what are these inputs and what is the probability of these inputs. That will be mentioned, otherwise we know what's the probability. Accordingly, we plug those values here and find the summation for all the input values, and we find the entropy. And next, the probability of output is equal to probability of input multiplied by the conditional probability of output. Okay, so here we know what's the probability of input. Probability of input is, or probabilities here of x1 and x2. What are the probabilities of x1? So generally it's a matrix. Probability of x1, probability of x2 is a matrix. And this we already know how to find here. And we just multiply these two matrices, we get probability of y. So this is the equation to find probability of y. Or sometimes we may need to find this or this term. I mean, with the help of this equation, you can find the unknowns. Then the entropy, the conditional entropy of input, how to find. So to find that, we first find there's a joint probability between x and y. So we have seen the joint probability between x and y is given by PD of x multiplied by the conditional probability of y. So this is a well-known equation from our previous lectures. So we also know what is PDX. This is basically a diagonal matrix for the input. So along the diagonal, we have the probabilities of inputs, and other elements will be 0. That is PDX. That's a matrix. We multiply with the conditional, I mean, outputs, conditional probability, and we get the joint probability between x and y. So if we know the joint probability, can we find out the entropy? Of course. So we just need to follow the general equation of entropy. Entropy is nothing but minus probability of input, I mean probability of any parameter log log of its probability. Similarly here, once we know px comma y, that is the joint probability, then we can find that. Okay. Then pxy, that's a conditional probability between x and y, is equal to joint probability divided by probability of the output for each output symbol. Okay, so this is a division here. So we have this matrix divided by these elements. So these are the individual elements from py. So here I have written some comment here, dividing each column by y1, y2, etc. So that is something like this. So if you have an output matrix py, we have y1 here, y2 here, is for y1, and this column is for y2, right? So this item y1 we are going to use here to divide, and next the second item y2 we are going to divide here. I mean, every element will be divided by corresponding column item. Okay, we have examples later on, but just giving you an idea. Okay, then the entropy yx is a general equation of the above term, that is probability, you know, so we find the entropy. And then mutual information between x and y is equal to h of x minus, this is a well-known equation, again we have used it earlier, that's from the definition of mutual information, that's equal to entropy of the input minus the conditional entropy of the input. Okay, so these are the different equations that we have. Some of them we have already seen, and we will be using these equations in solving the problems today. Okay, now we have some example here. So a channel is given here. It's a binary eraser channel. So we have the two inputs, x1 is 0, x2 is 1, these are binary. And we have three outputs, y1, it represents zeros, y3 that represents one, and y2 here that represents any confusion the receiver has. Maybe receiver does not understand whether it was 1 or 0, so we represent it as a question mark or an error here, e. Okay, one more information is given, that is probability of the inputs. They are equal to be 0.5, that's the probability of x1, and x2 are given. So with this information, we need to find out some parameters. We will see what those parameters. So the problem scenario is something like this. We have binary inputs and three outputs here. One is 0, other one represents 1, and other one here represents the error. So when x1, which is 0, is transmitted, it is received at the receiver y2. I mean, receiver's collection point is y2 with the probability of p, or it is received without any error with a probability of 1 minus p at the point y1. So this is basically the receiver. Receiver has three collection points, maybe three antennas to receive this, or three sub-channels to receive this, and so on. x2, which is a symbol 1, is transmitted, then can you all hear me?
Yes, sir.
Yes, sir.
Okay, thank you. Now we need to find out what from the channel diagram of the binary eraser channel shown here, you find out what? IXIYJ, that's equal to, I mean, specifically you need to find out what? I00, I11, I0E. So what's the meaning here? Actually, you need to find out the mutual information, but not for every case. Here, the question is mainly interested in finding out these I00. What's the meaning here? 00 means input and output. You transmit 0 and you receive 0. Probability of 1 minus P, right? And then I11, 1 is transmitted and 1 is. What's the probability? 1 minus P, right? And then the other case, what is 0E? You transmit 0 and you get E. What's the probability? P, right? So these three paths, even though there are many paths here, 4 paths here, we just are interested in this and this transmit 1 getting a 1, or transmit 0 and getting an error E. So these 3 we need to specifically find out here. Those mutual informations we need to find out here. So then the channel matrix, that's first when the channel is given, we need to find out the matrix here. I mean the conditional probability here. So we know very well how to find out when a channel diagram is given. So how to do that? So basically we have the input here x1, x2, and the outputs here y1, y2, and y3. So do we get this information here? First one, 1 minus P. Why? Because for from x1 to y1, that is 1 minus P. Next, x1, y2. That is probability where? Here to y2. Here, probability is P. Then x1, y3, what's the probability? There is no path going, right? So it's 0. Okay, then the second, x2 to y1, y2, and y3. So do we have anything from x2 to y1? No link, right? So it's 0. And other places we have those probabilities, we write that for y2 and y3. So this becomes the probability matrix for output. That's a conditional probability of output. That is written directly from this channel diagram when we know the probabilities. So next, what do we need? We know something here. Probability of output is equal to probability of input multiplied by the conditional probability of the output. So this is the equation we have seen today. Even earlier we have seen. So now probability of input, what is probability of input? That's equal to 0.5 and 0.5. This is given in the question that Px1, Px2 are 0.5. So from that we can pick these values. And then do we know this? Yes, right? We already found these values in the previous slide. So we just need to multiply P of x and P yx. That's a conditional probability, something like this. And when you just multiply these two matrices, that should give us the probability of output. So this is basically a matrix multiplication that gives us probability of output. So we have 3 terms here. So what are they? They represent y1, y2, and y3. So this is y1, this is y2, and this is y3. And then, okay, so probability of y1 is this, probability of y2 is this, and probability of y3 is this. This is basically from this matrix. We have found the value of this matrix in the previous slide. So these are the 3 components, because output has three 3 points, right? Y1, Y2, Y3. So these are the probabilities of that when you consider the output. Next, now we have the joint probability between X and Y. So that is given by the diagonal matrix multiplied by the conditional probability of output. Okay, so we know diagonal matrix is easy to write because it has a format that probability of the first input, probability of the second input, we need to mention here along the diagonal, and remaining elements are zeros. And this value we already know. And here, and next what we need to do is just multiply these values, I mean these two matrices, and that should give us something like this: probability of X comma Y. I mean, this is the joint probability between X and Y. And then conditional probability of X, Y. That is conditional probability of X when we know Y. How to find out that? This we have seen in the equation. In the list of equations I mentioned today, we have seen this. So that is equal to the joint probability matrix multiplied by the probability of output. So here we have what? This matrix is here. This should be cap X comma Y. And then to this matrix, we need to divide by P of Y. So P of Y has what? Y1, Y2, Y3. So basically we are dividing this matrix by P of Y to get this Pxy, or the conditional probability of X. So how do we do that? So if you write this matrix, and if you want to divide this by P of Y, we will be dividing every column by Y1, Y2, or Y3. So that means this one divided by Y1, 0 divided by Y1, 0.5 divided by Y2, 0.5 divided by Y2. Similarly, 0 divided by Y3, and this divided by Y3. That's what we do, because this is the column corresponding to Y. This is the column corresponding to Y2. This is the column corresponding to Y3. So we divide corresponding elements or corresponding column items and get the resultant matrix here. So conditional probability of X is equal to joint probability matrix divided by P of Y. So this divided by P of Y is here. So this element divided by Y1 and 0 divided by Y1, that is here. And the second column divided by Y2, third column divided by Y3. And then you just simplify these values. If you can simplify some multiplication, and then that should lead us to this value. Okay. And now we need to find out information of, mutual information between X and Y for some specific cases. This is what given in the question. I of 1, 1 or 0, 0, all those. Okay. We have the general equation here for mutual information between X and Y. What is that? That is equal to entropy of X minus the conditional entropy of X. So, but we are not interested in finding entire mutual information. We are interested in specific cases as given in the, as asked in the question. For example, we are interested in Xi, Yj. We are not interested in entire X. X has many inputs, X1, X2. Y has many outputs, Y1, Y2, Y3. We are interested in only specific cases of mutual information. Xi, Yj, what is that? That is information of input minus conditional information of input. So what cases do we need? So that is basically information is log of 1 by probability minus log of 1 by probability. So here, this gives us a general relation. So based on that, we will be finding out some specific cases. So this can be simplified because log A minus log B, that format is nothing but log of A by B. This is 1 by Pi and this is 1 by Pxyj. So it becomes basically log A minus log B format. So it's log of A by B. A is 1 by Pi, B is 1 by Px. So it becomes Pxi divided by pxn, I mean like this. Okay, now based on this general equation or general relation that we have derived for this specific example, we will find out what's the value of I00. You transmit 0, you get 0. So this is the path. X1 is 0, and at y1 you will be getting the 0. So how to calculate that? That is log of px1 y1 and x1. So this probability divided by this probability gives us the information x1 y1. So that is equal to log of 1, because we know these values from this matrix, right? X1 y1 xy matrix gives us this value, divided by px1. Px1 is what? That is 0.5 given in the input. So this value comes from the matrix pxy, condition probability. Maybe you can go back and check whether, yes, pxy, this matrix gives us different elements here. This is x1 y1, x1 y2, x1 y3, x2 y1, x2 y2, x2 y3. So those values we will be substituting. So right now we have x1 y1. That's what is being substituted here. X1 y1 is 1, and this is the input. It is given in the input question. The probability of x1 is equal to probability of x2 is equal to 0.5. We can see the graph that was given in the first part of the question. So from there we get this x1, that's 0.5. So it's basically log 2, so you get a value of 1 bit. The next part is the case 1 1. So that's what? Information of x2 y3. That means how do you get 1 1? This we have, I explained you at the very beginning of this question. You are transmitting x2, you are getting y3. Basically at x2 you will be transmitting y, and you will be getting 1 at y3. So your input is 1, that is x2, and your output is y3, that is 1. Okay, so we use the general equation that we have derived, that is log of p divided by the input probability. So we know this term x2 y3. So this is from the p xy matrix. If you need, again I can go back and show you here. Pxy matrix, we are interested in this x2 y3. So that value is 1, right? Yes. So where is that? That is here. So there is 1, this numerator is 1 divided by probability of input. It's given in the question that it is 0.5, so we get 1. Similarly, going to the next part, that is 0e. You are transmitting 0, but you get it as some error. So basically your x1 is 0, and you get error at y2. That path you need to follow. Okay, then so that's equal to what? This is the general equation, log of probability of this case, conditional probability of this case, divided by probability of the input. So x1 y2, that is again from the pxy matrix. X1 y2 is 0.5, and probability of input is also 0.5, since it is log base 2. Its value is 0. Okay, that is the question we discussed regarding binary eraser channel. We will see some complex examples, I mean complex cases or channels where we have a cascaded channel. So earlier what we saw is just 2 inputs, x1, x2, and 2 outputs, y1, y2. But now in this case, this is another example where we will be extending this channel y1, y2 to one more stage as z1, z2. So we have the original inputs here, x1, x2, and we get some output here at the intermediate point, y1 and y2, with some probability. Probabilities are mentioned here on the arrow, and then we also continue this channel. This is Z1 and Z2. They are the final ending points for the actual collection of data points at the receiver. So these are the intermediate points where we just tap out the output. So this is a cascaded channel because we basically combine two binary channels here. So one channel is here, X1 to Y1, this part is one channel, and Y1 to Z, Z1, Z2, this part is a second channel. So basically we combine these two. So this is a cascaded channel. So in this case, how to find out what? Find the channel capacity of individual channels, right? So it's basically combination of two channels. You need to find the channel capacity of individual channels and also find the overall channel capacity. How to do this? We will see, but we will be using all the common terms. I mean, PYX or PXY, all this we will be using. And finally, we will be substituting the channel capacity equation. Okay, so the first step, whenever you find the channel, something like this, is to find out the conditional probability of the output, right? So here, since there are two channels combined here, one from X to Y, other from Y to Z, we will call the, I mean, we will call the channel from X1, X2 to Y1, Y2, this part as the first stage, and the channel from Y to Z, it is Y1, Y2, Z1, Z2, that part we call it as a second stage. Okay, and then we will do the same process what we did in the previous example to some extent, because the question asked is here is something different. Okay, so first part, probability of, I mean the conditional probability of Y when you know X, that becomes this. Is it right? You see here. So basically, we are interested in here X1, X2, Y1, Y2. So how to write the conditional matrix here? Okay. So X1 to Y1 0.8, X1 to Y2 it is 0.2, X2 to Y1 0.2, X2 to Y2 it is 0.8. So that's the matrix here. Okay. 0.8, 0.2, 0.2, and 0.8. Okay, then the channel capacity is given by this equation for a binary symmetric channel. So this we have seen earlier. So capacity is equal to log n plus conditional probability of output. I mean probability of conditional probability of output log of probability, right? So this is the equation for binary symmetric channel, capacity of binary symmetric channel. So log n is what? N is the system that you use. I mean how many symbols you use. For example, a binary channel, we have two symbols, right? 0 or 1. For a ternary channel, we may have 0, 1, 2, 3 symbols, and so on. So let us limit our discussion only to the binary channel. So n value is 2. And you know the probability of these, how to substitute from this matrix, right? We know PYX, so YJXI, you can easily find out. So here you see the summation for J is equal to 1 to 2. And Xi is a common, I mean Xi is not varying, only Yj is varying. That means you are changing your columns for a constant X. For example, X1, what is Yj? Y1 is 0.8. X1, Y2, right? It is 0.2. So those things you need to consider here. Okay, then how to simplify? Okay, I have given some comment here for a common row. For this row, what are the J values? J is 1, J is 2. So when J is 1, value is 0.8, and J is 2, value is 0.2. Okay, so the values are substituted here, log 2, because n is equal to 2. It's binary, 0 or 1. So total number of symbols is 2. And then these values, probability, log of probability. So we have 0.8 log 0.8 plus 0.2 log 0.2. That's here. Similarly, the other one is the same. Okay, but we just need one row. I mean, for one common item X, we need different values of Y. That's equal to, I mean, when you compute this, it should be 0.278 bits per symbol. That's the channel capacity. Now, we are going to see the same for the next section of the given question. That is the second part of the channel. That is, X is the input, Z is the output. So basically, it is Y to Z, but our actual input is X. So the second stage, I mean, we are considering here probability of output provided you know the probability of inputs. So what is that? That is a combination of these two, X and Y and Z, right? So this is the first part of the channel, and this is the second part of the channel, right? Where Y is the input, Z is the output. So altogether, what that gives us XZ, right? So we are adding the second stage here. In the previous slide, we just saw the first stage of the channel between X and Y. Now we are considering the whole X to Z. So that's a combination of these two. So the first matrix we already know, YZ, 0.8, 0.2, 0.2, 0.8. Similarly, ZY, this also is the same. We can just go back and check from the given question. We are talking about this part, YZ. So Y1 to Z1 is 0.8, and then is 0.2. Then Y2 to Z2 is 0.2. Y2 to Z2 is Y2 to Z1 is 0.2. Y2 to Z2 is 0.8. That's what is the second matrix there. Yeah. Second matrix. This is the first matrix between X and Y. Okay. So this is again a simple matrix multiplication. So give us this value. We just multiply this row, this column, and you get it 0.68, right? So we will find out just one value, 0.8 and 0.8, 0.64. 0.2 and 0.2, 0.4. So 0.64 plus 0.4 is 0.68. Similarly, you just multiply. So you should be getting the probability between Z and X. And then find the channel capacity. Channel capacity is log n, probability of X and Z here. So this 0.68 and 0.32. Z1, Z2. Okay. Log 2, because we are dealing with binary, 0 or 1. So when you add up all these things, you should be getting the channel capacity of this whole stage as 0.0956. So that is the second part of the question. So now you can compare whether this value is better or this value is better. So when you just consider one stage, the value was 0.278 capacity. When you extend the channel to a bigger stage, I mean 2 stages, what is the overall capacity here? That is from X to Z. What's the capacity here? 0.09, right? So 0.09 is much lesser than the previous capacity. There is just one stage between X and Y. So, you know, so this gives us some general idea that when we extend the channel to multiple stages, of course, we will be compromising, that is compromising the channel capacity. We may regenerate the symbols at intermediate stages and make them more stronger, but the trade-off here is we will be messing with the channel capacity. We are having a lower capacity as you extend, but we may have still a better channel probabilities. 0.8 was there initially. We can still maintain that, or maybe sometimes we may improve that. But the channel capacity becomes a sacrifice. We need to sacrifice with this. So this is the trade-off when you consider a single stage channel or multi-stage channel, how the channel capacity and your probabilities are maintained or they get varied. Okay, so that is the end of today's lecture. And